review. I know it's a little bit long. Then we want to talk about the bra-ket notation. That doesn't make sense. Why is like this? Oh yeah. So last time, right? Not last time. I mean, very before last week, we already talked about every ket A has a bra, right? C times A. What is C again? Scalar, vector, or matrix? Scalar. Although I did not say it, you may think it's a matrix, but once you look at the bra correspondence, you see it is just a complex number, right? So it's a scalar. C times A becomes C star times A. And then we follow this distribution. And we remember A times B equal to A times B star. And what if we have the operator? How do we find their correspondence? We will discuss this. There's a new materials. The first thing I want to say is, if I have, let me follow the cat on the right. I follow the notes, okay? This one. What is X? I tell you, this is a matrix, okay? Because my purpose is to make matrix. What is alpha? Is this a bra or ket? And how about overall? Is this a vector, matrix, or a scalar? The whole thing, vector. This is very important. If you want to be smooth in doing calculation, you need to recognize this. Because you apply a matrix to my vector, rotate it, of course it is a vector. Okay, so the whole thing is a vector. So because the whole thing is a vector and it's a ket, then what is the dual correspondence in the bra space? Maybe you don't know, but it is equals to the bra version of alpha times the complex conjugate, complex conjugate transpose and complex conjugate of X. And from the right, then you might say, why is so strange? So let's do it step by step. This is bra. A bra is still a vector. Okay? And this is the matrix. Why is this? It makes sense if you look at the matrix form. Because this one, let's say I have 9 elements times 3 elements. It corresponds to 3 elements times 9 elements. Right? Because this one I can do matrix multiplication. Row times column, row times column, row times column, give me a vector. Here, row times column, row times column, row times column, give me a row vector. And then, of course, the operator needs to operate from the right. So you need to memorize this. And of course, the X is not just by itself. It needs to be transposed, followed by complex conjugate. Any questions? We will do some example later on this transpose, okay? Another thing I want to mention, right, I want you to know is if just linear algebra, a matrix times alpha equals to another matrix times alpha for all alpha. It means that I have an operator. You give me any vector, I apply to it, the result is the same as another operator applied to it for any of them. Then we are the same. Make sense? Oh, I did not say the conclusion. Then X equals to Y. Okay? Sometimes you need it in the proof. Now, there's also something sometimes confusing in terms of notation. Okay? X is a now operator if x times any vector equals to 0. Now, this 0 is not the basis state. I need to emphasize, but we follow what people do, which means equals to 0, 0, all 0, right? It's just the so-called a 0 vector. Sometimes they may write it as this. This is not the basis state, right? What is the 0 basis state in a 1 qubit? How do we write it in column? 1, 0. But here it is 0, 0. But just be careful when you see this. Okay? So this what it means is that you give me any vector, I always give you 0. I just destroy you. So this is not a good vector, right? But we still need to understand this. So let me just give you an example. For example, in 2D, I just make it sure 0 equals to 0, 0, okay? We are not talking about the 0 equals to 1, 0 basis state. Okay, just be careful, right? Of course, in exam, we'll make this clear, but when you read literature or read textbook, just be careful, don't get confused. Okay, so there are some vector will make all the, some make operator or matrix K will make all the vector become 0. So just disappear. You don't have this vector anymore. Okay, and what can that be? What will be the content of X? How do you construct X so that it gives you 0 whatever you apply to it? Just 0 everywhere. Yeah, that is one. Okay, good. So these are some basics we will learn later. Now I want to do something more important about this bra-ket notation. Number 4. So can you guess what this will look like in the, this is the ket, C alpha plus C beta. So let's try to understand what this is about. What is X in this context? Can you guess? Operator is a matrix, right? What is alpha and beta? What are alpha? Their state, their vector, right? They are ket. How about C alpha and C beta? Just some scalar, complex number. Exactly. Okay, so now I have a matrix. Just imagine, don't just look at this equation, a matrix, let's say square matrix, with a number, with a vector, which is a column. So of course, number times vector is still vector, right? Then vector plus vector is still vector. Matrix times vector is still vector. So the whole thing is complicated, it's vector, but this whole thing is still just a ket. If it's a ket, it must have its bra, right? So what can be the bra? Can you guess based on what we have learned so far? C star, bra of alpha plus C beta star, bra of beta, and then how about X? Transpose, complex conjugate, right? Well, this is called adjoint. We'll discuss this later. But apply from the right. Okay, you should have this in your cheat sheet for exam, right? But it's not difficult to memorize because if you put matrix on the left, you cannot do multiplication because this is a row vector. You cannot do multiplication. Okay, so this one is given. Then let's look at the last property, associates property. So that's what it says. If I have this, can someone try to understand what this is? I will think it as a ket, a bra, and then in the middle is a matrix. So what will that be? Then I apply the matrix to the vector. What is that? Rotation of vector. Not projection. Yes, that is very good. But I'm only asking about x times alpha. That is still a vector, still a ket. A bra inner product with a ket give you what? Projection, right? What is projection? Is this a scalar, vector, or a matrix? Scalar. So this is a vector. And then the whole thing is a scalar. Okay? I mean, you need to get used to this. Okay, so let's continue. I want to just say that, turn out that this is just like, it has the associative rule. The whole thing is like, yeah, you can say that this is like, I first do this x applied on alpha. That's what we just did, right? I can also say that I can first apply this to beta and then inner products with alpha. Okay, the linear algebra allows this. This is just the associative rule. You do use it based on your convenience and also use it to prove many equations. This is the associative rule. So let's prove something. Okay. Since alpha beta equals to beta alpha star. Do you remember this rule? Some of you forgot because it was mentioned here. The inner product between two vectors A and B equal to B inner product with A star. And that's okay. This is a complex number. You just say it's a complex conjugate, right? So I'm just quoting this equation, right? So I want to, then now, what I'm going to do is, if you look at this, right? I can say, let me say, sorry, I want to change the symbol. It will be better later, right? Let me call it, how about I call it x and y? No, x and y will be confusing. How about I call it n and m? It's the same, just number. N and m equal to m and n, m and n star, right? So if I say let m equals to x alpha, that's okay, right? Because this is just a vector. I use x alpha equal to this. And then what do I want to say? And then n, right? N and m. N equals to beta, right? I just try to use this equation here, okay? So what I'm trying to say, okay, m become x alpha, n becomes beta. So what I'm trying to do is just to say beta x alpha, that is n and m, right? Equals to m and n, but m in bra. But what is m in bra based on this? If m ket equal to x alpha, what is m in bra? Maybe I better just insert here, then m bra equals to alpha bra x dagger, right? And what is n in ket? Of course, this is just equal to beta ket, right? Which operation? Sorry. This one? Oh, no. This is the bra, right? I don't need to do anything. Its corresponding ket is just N. Make sense? You don't do any operation here. Okay? So just like this M, it becomes M bra. I don't do any operation. Alpha should become bra, but I do operation for the matrix and the scalar, not the vector. Yeah. So with this, then I plug in, right? I say beta is just equal to N. No, sorry, I want to use this one, right? M equals to alpha X dagger, right? And then N equals to beta, correct? I know this is a little bit confusing. What I'm talking about is here. This give me this, and then this give me this, right? Because this is M bra, so I just copy this one. N ket, I copy this one. I know it looks like I did not teach you well. But I still have this star. I should also put the star here because I'm using this equation. Okay. So this is complex number. I can also put the complex number on the other side. I mean, the complex conjugate. And this one, I will get this. This you need some time to go through and let me know if you have a question, right? But basically the conclusion is, earlier what we learned is Nm equal to Mn star. Now if we have an operator in between, beta operator gamma alpha, you put a star, you just swap. Like here you swap M and N, alpha and beta. But for the operator, you just put complex conjugate. Put the transpose and complex conjugate. So this is the equation that we will use. Okay. I know it's not straightforward, but think about that. Go back to think about that. Okay, so again, watch the video again, follow how I do it. I start with this, and then I define what is M, what is N. Then I will find the corresponding bra and ket. I just plug in, then I will get this equation. So, yeah, okay. So I want to move forward. Still have 2 slides. Probably can only finish once. And now I want to introduce something new called adjoint of a matrix. So what does it mean? So I have a matrix A, right? A. And its adjoint, right? Just its adjoint is A dagger. Okay, that is the adjoint of the matrix. What does it mean? It means you can apply the complex conjugate to it and then do a transpose. And that is its adjoint. If A dagger equals to itself, okay, it has an adjoint matrix. After I've done the adjoint equal to myself, then A is called self-adjoint. Or, instead of using called, we just say it's self-adjoint, or it is Hermitian. This is very important. Hermitian matrix has a property, you will see very soon, that it will have real eigenvalue. And later you find that for all measurement you quantum mechanics correspond to an operator. And what you get from the measurement are the eigenvalues of that operator. And since all measurement must have a real value, right? You measure the speed of a car, it's real. You cannot say negative I. So all the operator corresponding to measurement must be Hermitian. We'll do that again. But the main point is now you need to memorize this. Adjoint matrix of the adjoint of a matrix is just transpose and Hermitian and complex conjugate. If it's equal to itself, it is self-adjoint and Hermitian. Let's think of an extreme case. What if this matrix has only one element, 1 by 1? Then it's just a number, right? Then what is its adjoint? Just the numbers complex conjugate, correct? A number's complex, you can transpose the number, it's still that number, right? 1 by 1, right? But you do need to apply complex conjugate, right? So the adjoint of a number is just its complex conjugate. And now if the adjoint equal to itself, what does it mean? The number equals to its complex conjugate. What is that number? It's a real number. So adjoint is an extension of the concept of real number, right? So we learn the real number is just a subset of a higher dimensional tensor or matrix. Okay, so you can think it this way. Let's do some exercise that would be very clear. For example, let's say A equals to I01. What is A dagger? Well, based on definition, it's equal to A complex conjugate, then transpose, right? What's the complex conjugate of this matrix? Minus I, 0, 1. Are you okay with this? Right? Complex conjugate, you only flip the sign for the imaginary part, okay? What is the transpose? Minus I, 0, minus I, 1. Is A equal to A dagger? This is A. This is A dagger. Are they the same? No. So this is not a Hermitian matrix, okay? But this is adjoint. So let's look at another example. A equals to 0, negative I 0, which is just sigma y, the Pauli matrix we discussed earlier. What is adjoint? 0, negative I 0 star transpose, right? What is complex conjugate? 0, I, negative I, 0, right? But transpose, right? And you do a transpose, what do you get? 0, negative I 0. What is this? Still equal to sigma y, okay? So sigma y equal to sigma y transpose, so it is Hermitian, okay? Or it is self-adjoint. It is actually very simple, right? You just need to pay attention to the definition. You can ask ChatGPT when you need it. You can have a cheat sheet when you need it, but you need to appreciate what it is, right? You do the complex conjugate, you do the transpose. If it is equal to itself, it is a Hermitian matrix. This is a very simple operation. You just need to practice.